In the 25 years since Dr. Peter Glaser developed the idea of solar power satellites, not 1 kilowatt hour of energy has been delivered to the electric power grid from space. I believe the main reason for this is that most discussions of solar power satellites have involved the end systems that would be a result of 30, 40 years of development. Think of the reference studies of the 1970s, we're talking about 5,000 megawatt units, which are all very nice, but you have to kind of have a way to get from here to there. To get this technology moving, we need small pilot projects that can be designed and built, typically less than $100 million, and built in 2 years, so you can get someone like Dan Dalton to say, go ahead and do it. Once we get something up and flying and delivered to the electric power grid, this will change the mindset of a lot of people, just like the first flights of the DCX changed the mindset of a lot of people toward reusable launch vehicles. It'll also help us chart a development path for large-scale systems. Now, today, we're going to have, I think, most of the leading experts on space solar power in the United States here. Chairing our panel is going to be Dr. Seth Potter, research scientist at NYU, who's worked extensively in the field and has produced some of the most innovative ideas in space solar power.
David, thank you for that introduction. I think one of the privileges of chairing this session is that I've been able to develop a personal relationship with all the speakers this morning. It's appropriate that the person who's going to lead off is the person who has led off the idea of the solar power satellite. Dr. Peter Glaser, now retired Vice President of the Arthur G. Little Company in Cambridge, Massachusetts, is, as most of us know, the originator of the solar power satellite concept. He's done a lot of, time to switch to unpretentious mode. He's done a lot of stuff that we think is really cool, including project manager of the only experiments on the Apollo program still in operation, such as the laser ranging retroreflector. He's been on various NASA committees. He's formed the Sunset Energy Council, which promotes space solar power. Of direct interest to us, he is the director of the National Space Society, and I apologize to him for pulling him away from the board meeting, which began just a minute or two ago. He's also a fellow of the American Institute of Aeronautics and Astronautics and of the American Association for the Advancement of Science, one of at least two in this room, by the way. He's also a member of the International Academy of Astronautics and has more than 130 publications, books, and patents in the field of space technology, solar energy, and other space-related topics, including one of the books I find most useful, Solar Power Satellites, the Emerging Energy Option. I'm pleased to present Dr. Peter Glaser.
Thank you very much, Seth. The subject that I'm discussing actually will consist of three major components. One is, why are we still talking about solar power satellites? The second is, what have we done since the so-called large-scale SPS program of NASA? Briefly, just for those of you who may have forgotten what we have done, talk about it. And then the most important part is, what is happening elsewhere? If I have the slides, how do I get those?
Maybe John,
can you push the slides over for me? This slide is the basic slide to my talk. And if you talk about power from space, or solar power systems as it's now called, SPS, it is because of this particular problem we face on planet Earth, and that is exponential population growth. Next, please. There are three sort of interrelated real challenges here which we face as a human species, together with all the other species on Earth. And that is, we have to understand that there will be 10 billion people on Earth by mid-century, next century. And then, can you still leave that slide? Go back. And therefore, we are concerned with ecology, energy uses, and then, of course, the kind of resources we will need. And surrounding all this are those enormous amount of people on planet Earth. Next, please. Here I've shown two projections of population growth, one by 1991 by Dr. Hathaway at the IASA in Austria, and then the more recent ones. So we are going the wrong way, and more people living on Earth. Next, please. So what is it that we're about now? We are in the throes of planning a global economy. And the global issues are well known, they're discussed in various places: population growth, improvement of living standards, reducing the threats to ecology by various energy production methods, and then the availability of energy resources. For good or for bad, what is happening right now, right here, if we had the right equipment, would be known to some villager in China. The global village is a here and now. We call it the internet or whatever other means you want to apply to it. We have economic cooperation and competition, both of these happening at the same time. We have this global communication and information system, and therefore we are in the process of creating new things. And one example is ocean cities. We just had a conference in Monaco last November on this subject. Next, please. What isn't appreciated is that we're in the midst of the major population migrations. Today, 150,000 people have moved into cities. Please think of it. In 20 years, 250,000 people will move into cities. They have to have clothes, they have to have food, and they have to have water and housing. Now that is a challenge. If you want to know more about it, in June of this year, there's a city summit of the United Nations in Istanbul, where these things are going to be, during 1 week, discussed in great detail. Next, please. This is a reality you now find in places like Bangladesh. People have no place to live anymore. There, they move out into the delta. That is a problem we face, and there's one solution that we have to apply. And that is, without energy, for these people, they cannot exist. Next, please. Here you see the growth that is projected towards the end of next century, and the amount of energy we need. Now, in your own experience, you know how many children did your grandparents have, and how many children do we now have, and how much energy per capita was used by your grandparents, and what it is you use now. That is a real difference. And what we have to look for, how do we meet these needs? Next, please. A year ago, January, there was a meeting on space power systems in Albuquerque. And I had a session there, and I invited a Russian engineer from Moscow, who's studying the energy aspects. And these circles just indicate how many gigawatts are being produced in various countries in, please note, Eurasian continent. used to this kind of thinking. And Europe is still very large, but that's a small population. Now imagine all these other countries, India, China, Indonesia, Southeast Asia, where most of the population of the world will live, will have to get to the same point that we have in Europe and the US during the next century. Next, please. If you just look at coal, by 2020, 50% of the total coal demands will come from, energy demands will come from coal. In developing countries, in the emerging economies. Next, please. Now, will it last forever? Of course not. Even if it would, it is very unlikely that we can burn fossil fuels on the scale that we need to do it. Will there be oil? We have passed the major availability of oil and other fossil fuels. Energy economists are aware of these numbers. And we are now on the downslope. Now that is a new experience for us. We will never run out of coal, oil, or gas. Just as we will never run out of gold or diamonds. All it means we're going to pay a lot more money for it. Next, please. What were then the motivations for power from space? Advances in science and technology, I'll briefly talk about those. International Space Station, evolving concepts, and planning for the global economy. Those are the real issues we are facing today. Next, please. The beginnings of wireless power transmission didn't happen too far from here on Long Island. In the early 1900s, Nikola Tesla was convinced that global power transmission was the way to go. By the way, Nikola Tesla also holds the patent on wireless radio, not Marconi. It was awarded by the US Supreme Court to him in 1940. Next, please. The microwave generators, which were invented back in Raytheon days, called the radar range, today microwave ovens. There's 300 million ovens in use. This is an article of commerce. They're efficient, about 90% efficient, and we now know we can make it in terms of solid state and far more lighter weight things than we knew even back in the early 70s. We also know a great deal about safety of microwave power transmission. You know, we're concerned about electromagnetic forces and high power lines. There are about 200 papers on EMF concerns. There are 13,000 papers on microwave concerns. Therefore, we know a great deal. Next, please. About 30-odd years ago, the dipole rectifier was developed. We know that we can convert these microwaves directly into DC with 90% efficiency. Next, please. The first microwave power transmission occurred in 1964 at Raytheon. Bill Brown had a helicopter flying, demonstrating that you can transmit power. Next, please. The Canadians were convinced that was the way to go in communications as far as they were concerned up in the North Country. And SHARP, the Stationary High Altitude Relay Platform, was their project. Next, please. And they flew these things. You can see the antenna sort of in the tail. Next, please. We are interested in these high-altitude, long-endurance aircraft. I call them the poor man's communication satellite. These are the ways that we can find various applications for wireless power transmission which are near-term. Next, please. Now, here is a famous NASA SPS reference system. I call this the bridge building era of solar power satellites. It was very large and certainly not whatever would have been built, but it had a specific purpose. And the purpose was to assess the technical, economic, and societal issues. And it did not matter that we had a design which would never be built. We could exercise all of the kind of things we needed to in this case. So it was a very important NASA project in the 1970s, and then DOE got into the act as well. Next, please. We learned about the receiving antenna, which could be on the ground. Now, it so happens that it's partially transparent, therefore we don't make a desert beneath it, as would be the case if we would have solar panels. Next, please. And here is sort of the final size concept using the 1960s technologies, mind you, for solar power satellites. We'll never build one of those, but it is a useful example of what we were talking about then. It was very large, very heavy, and required a huge amount of support in terms of launch systems. At that time, we didn't even begin to talk about lunar materials. Next, please. A lot of work went into trying to understand the safety of operations. For example, at the fence line, we have exposure about the same as if you're 4 feet away from a microwave oven. Now, we don't expect people to live at the fence line, no more than you put your bed next to a microwave oven. Next, please. We already then realized that if we launch, we may want to launch from ocean bases rather than land bases. Land is rather expensive, and people don't like to listen to launch system taking off, even in Florida. Next, please. So what we looked at were the receiving antennas, which were offshore. And that just gives you an idea of the size based on the typical antenna of a 5 gigawatt received on Earth. It's located in the ocean. Next, please. You see the antenna supported by pylons, and the fish farm there, because now we have an artificial way of maintaining huge fish supplies. You know, when you buy salmon nowadays, it's coming from fish farms in Norway, no longer from people who fish for it in the West. Next, please. One simple thing that we have is that we can build these now with accreted foundations by having various small current go there, various things, then accrete, and in a few years you have a very good concrete support system there. Next, please. This is a system for dipole rectifiers encapsulated. Yeah, of course, they're solid state. Next, please. And now they're supported at the right distance from each other by these pylons. Now, this was discussed, next, please, at a conference in Monaco last November. And there was an estimate made of how many cities around the ocean would be required by the end of next century. And those dots you see there are the cities. And these cities will require energy. And the energy may well come from space by then. And that's when we have up to these 14 billion people living on Earth. Next, please. People just cannot visualize that you can, by wireless power transmission, convert microwaves directly into DC with a reasonable efficiency. The most important experiment during the SPS concept development and evaluation program which was a NASA DOE program, was to use a Venus site in order to demonstrate that we can convert microwaves directly into DC. Next, please. And that's a 30-foot diameter dish which was used and we beamed across 1 mile. The receiving antenna on top of that mountain. Next, please. You can see this was the antenna, and we were able to achieve 82% conversion. Next, please. Here are the results of the assessments. You know that there's nothing that was found that would have precluded us proceeding with solar power satellite development. Next, please. The first international meeting took place in the Netherlands. That was the output of the meeting on solar power satellites by the International Microwave Power Institute. By the way, the subject will be discussed in Boston at the end of July. Next, please, this year. The Japanese were very interested. Again, it's an early version of what we had in this country. Next, please. They had delegations come to visit us in this country, shared with us the results of their R&D. Next, please. An important meeting took place in France in '91, in Paris. Next, please. During the International Space Year, the students at the universities of Kobe and Tokyo had a MIROX, microwave lifted airplane experiment, and they flew this little model airplane. Next, please. And here you see it flying, all solid state devices. So they were very interested and continue this interest to this day. Next, please. The next thing that they did, which was not really well publicized, they had a rocket which had two things. One is they had a satellite with the receiving antennas, and the rocket itself had the transmitting antennas. The next slide. These are the transmitting antennas, solid state, which are deployed in this particular photograph. Next, please. Just the top view. Next. And here you see what happened in space. 800 watts were beamed from the satellite, from the rocket, to what they call a daughter satellite. And that was done to establish the effect of plasma on wireless power transmission, and there was no effect. Next, please. This is the SPS 2000 project, which is being designed to beam 10 megawatts back to Earth. Again, this is an exercise being done by the Institute of Space and Astronautical Science. On that particular exercise, the working groups were established with participants from Russia, Ukraine, from France and other countries, England, the UK, who all are interested in seeing such a project happen and get underway. Next, please. This is not just paper stuff. As you can see, structures were built to understand the implications of that. Next, please. And then they had a public tour of a model of SPS 2000 in science museums in Japan and I believe in other countries. That is the top part. Next, please. And it is a house and it had various power using equipment showing how it worked. Next, please. The Russians were very much involved in all of these things, as I mentioned. And in 1985, for the first time at the International Astronautical Federation Congress, they shared with us their plan to develop SPS. Next, please. One of the first things they were going to do is to deploy a mirror to reflect sunlight, for a reason that I'll explain in a few minutes. This is a very important experiment. Next, please. And this is a picture of the mirror that was deployed. So they were really on target with their experiment at the time. Next, please. Mir space station in '94 beamed power to a Swedish satellite. Now that was a major successful experiment. I couldn't understand why people didn't really knew about it in this country, as if the rest of the world didn't exist. Next, please. There's one other way that we can use wireless power transmission, and that is to access our renewable energy resources, again for the same reason that I mentioned before. That is, energy sources, ecology, and energy uses. Next, please. We used as a source the hydroelectric dam on the Guri River in Venezuela, which will produce 17 gigawatts in 2000. Next, please. The way this was done, also with a reflector for microwaves, power relay satellite from a place where we had our renewable resources to Europe, because the European community wanted to have 25 gigawatts available in 2025. And they did not have renewable resources, which was what they wanted. Next, please. So here you see a very quick overview of all of the various things that have been worked on. I didn't mention point-to-point transmission. That was done at California and is now being done by Kansas Electric Company. But this is being done all over the world. And I'm delighted to say, after a hiatus of some 15 years, NASA is relooking this project. Next, please. So what is then the vision we have? SBS, in whatever form it will take, and various countries have their own ideas, will have to be in a reality in terms of economic and political issues that have to be faced. It has to be acceptable to people on Earth, and actionable by industry and government. And I believe that we know enough to say that this is one of the major options as compared with fossil fuels and even nuclear power, which is being considered very seriously by these countries who have not this option ready in the foreseeable future. And I leave it to your imagination if we would produce as much power by nuclear power without having the major problems resolved of what do we do with waste and what are the costs of decommissioning nuclear power plants and how do we ensure safety. Next, please. So this is where we are at. I've tried to very quickly give you some of the highlights. For those of you interested in literature, you can go and find every month, just about somewhere in the world, a major meeting on the subject. In this country, you can come to the World Future Society meeting end of July, which will be held in Washington. The Inter-Society Energy Conversion Engineering Conference holds its conference in Washington in the middle of August. We'll be discussing this. There'll be a conference in Kharkov, I think also in the fall, and in Moscow in November, and next year Canada. There is no excuse for people to say, well, we never heard about it. Well, all I can say is, have you learned to read English? And it would help if you read Russian, Chinese, Indian, Japanese, etc. Thank you very much.
We have time for one question. I'm sorry, I'll have to limit it to that because I want to allow Dr. Landis to finish by 9. Anybody?
Yeah.
Do you think that this technology could be driven by the free market as opposed to government?
I believe that's the only way it will happen. Governments, I think, can help during the R&D phase, just like NASA is expecting. But in the end, particularly in the free economies, and most of these countries have free economies, we will have to do it by entrepreneuring, starting in an appropriate way. And I will tell you, if you look at where the Wright brothers started, they flew 100 feet. And it wasn't government that really made the aerospace, the avionics industry work. What the government did do, particularly in this country, as the NACA, we need the equivalent of an NACA in order to produce solar power satellites. Thank you.
Thank you, Dr. Glaser, for setting the tone of this morning's session. My next speaker is Dr. Jeffery Landis of the Ohio Aerospace Institute on permanent assignment to the NASA Lewis Research Center in Cleveland, site of last year's ISDC. Dr. Landis has published over 100 scientific papers in the fields of photovoltaics and astronautics and chairs the Vision 21 conferences. He's also a Hugo and Nebula Award-winning science fiction author, having written over 40 short stories and novelettes. And on a personal note, I'll say that much of his work on solar power satellites was the inspiration for some of my work. So I will turn the podium, figuratively speaking, I guess, over to Dr. Landis. Jeff, if you want the microphone, I think this thing comes with it. You don't have to be a rocket scientist.
Thank you.
But don't you wish you were?
I wish I could say one.
Well, I have to admit that it's a tough act to follow, Peter, but I'll see what I can talk about, maybe at a little bit different level. One effect that Peter didn't mention, but is of course very important with the burgeoning world population, is the fact that it's been well known for over 100 years now in economics that as the population becomes richer, the population growth becomes smaller. So the richest countries in the world, America, Japan, Western Europe, are the ones with the lowest population growth. So I think another reason that it's important to have large energy supplies available everywhere in the world, not just in America, but in the third world, India and South America, is that if we can bring the rest of the world up to the American standard of living, we may not have to worry about this 10 and 20 billion person population of the world. In fact, possibly we could say this is the most important project that we could possibly work on, is to bring all of the world up to the highest possible level of richness. Let's all get rich. Okay, you, I'm sure, all familiar with this concept, and I think Peter may have shown this exact slide. This is the 1980 reference baseline solar power satellite, and the object of this design is to take solar energy in space, where it's abundant, and beam it down to the Earth using a microwave beam. I'm going to look at various different options for such a solar power satellite. And this is just another view of the solar power satellite. If this is in focus and you have good eyes, you can see the key thing about this is it's very large. This is 16 kilometers from end to end. And this is the transmitting microwave dish. It is 1 kilometer across, 6/10 of a mile for those of you who are not yet metricized. That was the baseline concept, but let's look at some other things. These are some other concepts that were looked at around the same time. Various solar thermal concepts. These are essentially steam engines in space. This one's 18 kilometers across, 10 kilometers across. Even the idea of putting a nuclear reactor up in space, which seems an odd idea, because some people think that nuclear reactors shouldn't be down here on the ground. This whole system is 2 kilometers across, and some various versions of the photovoltaic concepts that are up to 32 kilometers across. These solar power satellites are roughly the size of Manhattan. They are very large objects. Looking at, this is the Rockwell reinvented concept, where they continued looking at Rockwell, and they moved from the baseline up to a somewhat more advanced concept. This is, in fact, even bigger. This is 28 kilometers across. I just want to emphasize that we're talking some relatively large-scale projects here. I suppose I don't need to mention that they're relatively complicated to build. Sure, you can ask questions if you want.
What time frame is this? What, around early 80s?
Well, yeah. This is, the one on the left here is the 1980 version. The one on the right here is one that they finally published around 1990. The work was actually done, I think, around 85, 87. And the interesting thing about these is this is a cost analysis, again, from Rockwell, the original solar power satellite, which comes in about $3,000 a kilowatt in 1979 dollars. $3,000 a kilowatt sounded like a good power price when in 1978 people believed that power prices were going to exponentially increase and come up to incredibly huge numbers. Even the reinvented version, and this is, these power satellites are being produced at a cost of about $30 billion each. Even the reinvented version is about $1,500 a kilowatt. $1,500 a kilowatt, for those of you who know electric pricing for primary power plants, is an okay price for a capital power plant. But it's not a great price for a capital cost for a power plant. It's not something that people are going to jump up and down and say, wow, is that cheap? And that's very unfortunate, because unfortunately, no power company in the world is going to spend $30 billion of risk capital in order to get an okay price for power. We need to do a lot better than this if we're going to make power feasible. Well, first let's look at that first question. Why the heck are they so big? The reason that they're big is they're far away. The solar power satellite concepts have been put in geosynchronous Earth orbit, which is uniformly known as GEO among all rocket scientists. The reason that they're in GEO, roughly 36,000 kilometers away, is three really good reasons. The first one is that GEO doesn't move in the sky. So if you can ever see your ground site, you can always see your ground site. That means that your utilization of the solar power satellite is 100%. If you have a $30 billion asset, you want to be able to use it 100% of the time. That's a good reason for being in GEO. The second is there's no tracking even. It doesn't move in the sky. So your ground receiver is always pointed at the same place to get your power. The third good reason is it has almost continuous sun in GEO. It's far enough away from the Earth that the satellite doesn't really cross the Earth's shadow. In fact, it does. It crosses it for up to 69 minutes, which turns out to be 35 minutes before and after midnight at the equinoxes. That, in fact, is beginning to be marginally unacceptable. Power companies who want continuous power. But it's still not bad. It's not a whole lot of loss in sun. Unfortunately, there's two huge drawbacks. The first drawback is it is 36,000 kilometers away. That's a long way. The second is, being that far away, it's very hard to get to. It's expensive to put things in GEO. It's much easier to put things in low Earth orbit. So over and over again, when people look at the solar power satellite, the first thing they do is say, well, geez, let's not put it in GEO. Let's put it in low Earth orbit. We can get to low Earth orbit. Take the shuttle to low Earth orbit. It's easy to maintain. Easy to get to. So let's look at some better orbits. How about low Earth orbit? Low Earth orbit, which is uniformly known by rocket scientists as LEO, is roughly 150 kilometers, which is about as low as you can go without dropping down due to drag, up to a few thousand kilometers. It's easy to get to, relatively easy to get to compared to other orbits. Unfortunately, utilization fraction is lousy. You can't see very much in low Earth orbit. I'll get back to this in a second. But I want to show you just one example of a low Earth orbit solar power satellite. This is a picture that came out of NASA headquarters. And they said, like dozens of people have said before, well, let's not put it in geosynchronous orbit, let's put one in low Earth orbit. It will look like this, and you get to it with the next generation space shuttle. And here you can see the microwave antenna and a huge sort of tower in gravity gradient mode of these concentrator devices that focus light onto the little receivers and send it down a cable to the satellite. Well, well, what's wrong with this picture? Well, I'll tell you what's wrong with this picture. It's that your utilization fraction is horrible. Let's get this right. It turns out that you can't use a rectangle all the way down to the horizon. If you beam through too much air, if you beam through a low enough angle, your efficiency is going to drop down to very low numbers. I picked, just for the sake of this argument, 45 degrees. You can see a satellite and beam efficiently if it's within 45 degrees of the zenith. So just look at these numbers. You can see this is, I think, a 1,200 kilometer orbit, a pretty high low Earth orbit. This is the pictured scale. If you want to beam to off the equator, you're going to have to go in a polar orbit because you can't see anything. In fact, from the equatorial orbit, you can't get to North America at all. But what you can see is the amount of the ground that you can see from one of these satellites is very small. Look now at this visualization. This shows a satellite that's moving in a polar orbit, and I've taken these pictures 9 minutes apart. So this is what you can see from the satellite every 9 minutes. And just picturing this one where it's over North America, this is the 45-degree cone. This is all of the places in North America that can see the satellite within an angle of 45 degrees over the zenith. So what you see is you can see this particular satellite from a particular ground station for 9 minutes, twice a day. Okay, you're getting 18 minutes of power out of the satellite. Unfortunately, that's a horrible utilization factor. Nobody really is going to want to make a satellite that you can only see for such a short period of day. Another example, 500-kilometer orbit, which is the orbit that was in that picture I just showed you a little bit earlier. You need 360 satellites to get continuous electricity at one site. Unfortunately, that's just too many satellites. If you're trying to make it cheaper by making it smaller, it doesn't work if then you have to make hundreds of them. Well, if you move higher up, then you need fewer satellites. But unfortunately, you have other problems. This is a view, actually, of the other problems. This is the radiation in Earth orbit. And as you can see, as you get up to a little bit over a couple of thousand kilometers, all of a sudden your radiation just jumps up hugely exponentially. You're getting into the Van Allen belts. The Van Allen belts are a couple of Earth radius, 1 Earth radius to 2 Earth radius away from the surface of the Earth. Well, that may not be a problem. There are potential solutions to radiation tolerance, but you still don't get continuous coverage. You still need lots of satellites. Well, this geosynchronous orbit, of course, that's great. It's far away. There's another option that people really have not looked at previously, and that's, well, what if you go even further away from geosynchronous orbit? The first thing you'll say is, well, that's silly. If geosynchronous orbit is bad, then if you go further away, it's even worse. But since I have a kind of contrary nature, I looked at that in some amount of depth. Well, let's look at the question of how do we reinvent the solar power satellite to make it better and hopefully cheaper. There's really 3 approaches to doing this. We can either find a way to make big apertures and make these things that are kilometers across without the big high cost. Maybe you can make things that are the size of Manhattan without being hugely expensive. The second is maybe we can use a shorter wavelength. I hope you all are familiar with the wavelength aperture law, which says that the shorter the wavelength, the smaller you can make the aperture.
Jeff, excuse me, I'm going to get into that. So
Okay, good.
if anyone wants to know,
Good. And the third is to just accept the large system size. Say that, well, okay, these are very large systems. So if I had the time, I would talk about 3 new concepts to do this: big aperture, short wavelength, and large system size. Unfortunately, I have probably about 2 or 3 hours worth of talking, and I have to get through it in only half an hour. Well, looking at the large aperture, one way to do this is to look at lower cost systems. This is just some work that we did, or at least funded, at NASA Lewis on the idea of a low cost, very lightweight solar cell, where the idea is you make it low cost and lightweight and just don't worry a whole lot about the efficiency. This is one of the little test samples of these low cost, lightweight solar arrays. They're, as you can see, very light and flexible. It's amorphous silicon. This particular one I put under the solar simulator, and it came in at about 4% efficiency. Not terribly good. They make amorphous silicon arrays at about 12% efficiency. Amorphous silicon may not even be the best material for this ultra-light, ultra-thin solar cells. Here's a couple of other materials with the chart of how efficient they are versus time. You want to look at the right-hand scale, which is air mass zero space efficiency. And you can see that over the last few years, these two materials, copper and diselenide and cadmium telluride, have been increasing efficiency at a relatively incredible clip. So one of the possibilities to use these solar power new materials is to put them out in relatively large arrays, in fact, relatively huge arrays. And then an interesting thought that goes along with that is possibly you can integrate the transmitter directly onto the solar cells so that instead of having a solar array and a microwave transmitter, you have them together. A solar array that transmits microwaves. And there's other possible configurations. For example, if these are so light and so cheap, then you don't necessarily have to make them in the form of plates that are etched onto the sun. A sphere has really only 4 times as much area per unit cross-sectional area as a plate. So if you can accept the loss by a factor of 4, you could just make a big sphere, which has the interesting advantage that it doesn't have to really track the sun, that regardless of which way you look at a sphere, it's always round. Well, I'd like to drop back a little bit. I'd like to talk about that idea a little bit more, but for lack of time, I won't. And I'd like to give you a little bit of a tutorial about what solar cells have been doing in the last 20 years. For a solar power satellite, we need to really have improvements in 5 different parameters, not just the efficiency and the weight, but also radiation tolerant, because we want the solar cells to last for a long time in space, and also high volume productivity. I'm just going to look at a couple of these issues. Single crystal solar cells have been getting a lot better in time. These are some records. Actually, this is about a year-old slide, and it's a couple of better numbers. But gallium arsenide solar cells are up to a little bit over 22% efficient now. Indium phosphide are highly radiation tolerant, and they're up to almost 20% efficient. The best silicon cells are, in fact, coming up toward the gallium arsenide cell results. They're a little bit over 20% efficient, as opposed to the stuff that's flying in space at the moment in the way of silicon cells, which are about 14. So you can do a lot better than what they're currently using on satellites. Unfortunately, the advanced silicon at over 20% is not radiation tolerant. They tend to degrade in space. But we can do even better than this efficiency. We can look at solar cells where we have 2 different materials that use the spectrum even more efficiently. We have a top cell that uses the blue part of the spectrum, and then a bottom cell that uses the red part of the spectrum. And then we can get higher efficiencies. Yeah. We can get efficiencies of 25% with these 2 junction cells. They're in fact now being made. They're going to be flying in space relatively soon. The efficiencies are about 20% for the actual manufacturing ones. But I talk to the people who make these every week or so, and they're relatively confident that they're going to be flying 22 and 23% cells in the next couple of years. We can do even better than that. We can concentrate the sunlight. If we concentrate the sunlight, it turns out efficiency goes up even more. This is the record for efficiency. It's a little bit over 30% for a 2-junction cell with gallium arsenide and gallium antimonide. So just keep that in the back of your mind, that you can do very high efficiency, but it's going to cost you. High efficiency cells are expensive. Okay, there's one other thing that I'd like to just toss out for you to think about. I've talked to a lot of solar power and space enthusiasts, and they all seem to think that ground-based solar power is a competitor. That ground-based solar power is evil because we want to put solar power in space. Not true. Ground-based solar power is satellite solar power's best ally. There's a couple of reasons for this, but the big reason is you've got to shake out solar power technology. You've got to get a technology that can be produced in huge amounts. with high efficiency and that has all the bugs worked out of it, because until you have a reliable, cheap technology on the ground, you're never going to have that technology in space. So you ought to start thinking of satellite solar power as being an ally of ground-based solar power. Let's take a look at world PV shipments. Every year I add another point to this graph, but this is how much solar power is being shipped on the surface of the Earth. About a third of this is built in America, by the way. And you can see it has a sort of slight curve upward, but the current shipments are about 80 megawatts per year. The solar power satellites we've been talking about have been about 5 gigawatts, 5,000 megawatts. So it's going to take probably another couple of decades before world production is up to the rate where we can turn out a solar power satellite. This is another reason why solar power on the ground is relatively important. Well, so let's look at that question. How can we interface solar power on the ground with solar power in space? This is one view of a curve of how much power is needed versus how much power is being produced by solar power plants. This is the amount of kilowatts that are used in a particular place in California in the summer. So it's a power use curve. And what you see is this sort of dark area is above the baseline load. That's the expensive power. A power plant on the Earth in general wants to produce pretty much constant power. And if you have to produce this peaking power during the daytime, that costs more. So this is the power that you really want to provide to the user. And what you can see is this is a photovoltaic array output, average and a peak day in the summer. And what you can see is, in fact, it's not a bad fit to the peaking power. It's not a great fit, but it's not a bad fit. And if you do the numbers, it looks like about 10% of the US electricity could be supplied by solar without any particular cost to the fact that you only get solar during the daytime. And that's interesting. That's 10% is a lot of power. This just shows one particular solar power plant. This was Glaser, which was the first megawatt scale power plant. If you have very good eyes, you can see a little house here and a little pickup truck that just shows that this is in fact pretty big. We can compare that if you want to the largest space solar arrays ever built, which are large compared to a person, but they don't dwarf a house. So what's interesting is you can certainly imagine solar power on Earth coming up to the point where it's providing 10% of the electricity for, say, America, without any real problems with the fact that it only happens during the daytime. And then that's sort of a limit, isn't it? Because once you start getting more than that, people are going to want their power at night too. So you can see the solar power on Earth as in fact building up the market for solar power in space. It's getting people hungry for solar power, saying this is great, and then saying, wait a second, we need it the rest of the time. So what can we do? Well, the first thing that would be relatively easy to do is to integrate a rectangle right onto a solar array. Peter Glaser, in fact, mentioned that the rectangles are semi-transparent. So in fact, it wouldn't be very hard to make a rectangle that, in fact, is also a solar array. Well, where might you put it? You want power at night if you're going to use ground-based solar as an ally instead of as a competitor. So you could imagine a system where in the daytime it's producing sunlight electricity, and at the nighttime it's producing space electricity. Well, where is the perfect place to put that? Where is the spot that you would put a solar power satellite and have it illuminate the Earth at night? Well, it turns out there is a spot, there is an orbit in space that looks at the nighttime of the Earth relatively continuously. This is the trans-Earth Lagrange point. Technically, it's L2 in the Sun-Earth Lagrange system. It turns out, unfortunately, it's 1.5 million kilometers away. That's about 35 times further away than geosynchronous Earth orbit. But that's okay. We can live with that. We can pick, by the way, a halo orbit around L2. The reason is, of course, exactly at L2 is in the Earth's shadow. The Earth's shadow, however, is very small, 1.5 million kilometers away. We can make an orbit around it. It turns out that orbits around these Lagrange points have been demonstrated by satellites. And they're very easy. They take only a kilogram or so of station-keeping fuel per year. It's an unstable Lagrange point, but it's a horribly high order instability. And you really do not need much fuel to keep yourself in that orbit. Well, what are the advantages of this horribly distant orbit? Well, it is a continuous sun orbit. There are no eclipses, not merely only eclipses for 69 minutes a day, but no eclipses at all if you're in the halo orbit. An interesting, different advantage is that its sun angle is always a constant angle to the Earth pointing, whatever this angle is, and it would be very small. It would be half a degree or a quarter of a degree. So the interesting thing is that we saw these earlier designs for solar power satellites, and one of the sort of interesting, complicated pieces of machinery is the fact that they need these rotary joints. Well, all of this complicated machinery sort of over here to steer the beam, and you wouldn't need that if you were in the Lagrange point, because you're always pointing at the same spot. The sun is one place, the Earth is a quarter of a degree away, and you can just fix that angle. This makes, in fact, the solar power satellite design much easier. Another thing that makes it easier is that there's almost no external forces at this point. There aren't any tides, there aren't perturbations by the moon, the Earth tidal forces are almost zero. But the other very interesting thing is that it's a continuous view to the night side of the Earth. It's always looking at the night side. So let's see if we can't do a little bit of a preliminary design for such a satellite. And the first thing that I'd like to point out, in fact, all of you that follow the shuttle missions will have seen the Lagarde design for an inflatable concentrator fly. These particular numbers came from a Lagarde 16.5 meter inflatable antenna, and they claimed it's very cheap. They could do it for 15 kilograms. That is a big antenna for 15 kilograms. It's inflatable. It's just thin plastic as the structural material. So if we can do that, we could make a solar array for 24 kilograms with a 9 kilogram focal plane array, and we could use these expensive solar cells and get these very high efficiencies because we're concentrating the sunlight down onto a very small solar cell. This was a chart for an earlier presentation where I was talking about whether it's possible to use solar cells at Jupiter. Ignore that. Anyway, another possibility to use a balloon and silver on the inside, but we don't even need that because these Lagarde concentrators are so good. These inflatable concentrators are tremendously structurally efficient materials. Well, what else can we do? Well, it turns out since sun pointing and earth pointing are almost the same, we can use the same concentrator system for both the microwaves going to the earth and also to concentrate the solar energy coming from the sun. So essentially, you're halving the number of components, and you can make a solar power satellite that has no moving parts whatsoever. So it turns out, if we do this particular position, where we're always beaming sort of back directly from where the sun comes from, the simplicity of the design becomes much simpler. Well, and I sort of apologize for the relative roughness of the sketch. I was in a little bit of a hurry to get here. This sort of shows in concept what it would look like. You have these concentrators. They concentrate sunlight to a little receiver. The receiver would also have built in the little solid-state microwave transmitter, which is very slightly offset from the sun pointing concentration focus that sends the microwaves back out that get beamed to Earth. Well, there's a couple of other little things you might want to do. The first thing is, since it's 35 times farther away, either you need a 35 times larger receiving antenna, or else you have to really work hard at what you do. One concept is to, instead of making just a circle, make a circle with these airy rings on the outside. What this does is it flattens the profile of the microwave beam at the receiver, and and that allows you to have a little bit less unused area around the edge. And each one of these little rings would consist of a myriad of these 16-meter dishes. Looking at some numbers. Okay. The other thing we can do is we can raise the transmission efficiency by making a higher wavelength. Instead of using the 2.45 gigahertz to 3 gigahertz that was assumed by the original solar power satellites, we could go up to 30 gigahertz. If we did that and we had 33,000 of these 16-meter concentrators, then we would fill essentially the same as a 3-kilometer dish. And 3 kilometers is pretty small, in fact, when you think about it, compared to the 18 kilometers in some of the reference systems. Even though this system is 35 times further away, it's not particularly larger. It's not larger because we're using the same aperture both as a transmitting antenna and also as a solar receiving array. But the part of it is to move up to transmission frequencies that just were not available 20 years ago. Nobody could do 30 gigahertz 20 years ago with any sort of reasonable efficiency. To take a hit on that, if you're looking at 35% photovoltaic arrays, which are these expensive cells that I mentioned earlier, if we're looking at millimeter waves, that is 30 gigahertz, we can really, with today's technology, only expect about 30% conversion efficiency of electricity to microwaves. They're not nearly as good as the magnetrons that we're talking about. But that still gives us a gigawatt of power. A gigawatt is a large power station. These days, in fact, hardly anybody makes power stations as big as a gigawatt anymore. Now they make these natural gas-fired turbines that are a lot smaller. But that's okay. A gigawatt power station is the sort of power size that power companies are very comfortable with making. And if we were to move, in fact, the centimeter wave efficiency, this would be a 2 gigawatt plant. The centimeter size efficiency would, the centimeter size wavelengths would make the whole thing about 10 times as big physically. So if you did that, you'd either have to use a much larger receiver or a much larger antenna. I didn't type this. In fact, if you have 6 hours of beaming per site, which is the 45-degree angle, you need 4 ground sites. But 4 ground sites isn't a huge number either. I think it's very reasonable. So that really is a quick summary, and unfortunately I'm out of time, of some of the reasons that you might want to look at other orbits than geosynchronous. And in fact, a reason why it looks like, in fact, a super-synchronous orbit, the Trans-Earth Lagrange point, might be a very interesting place to put a solar power satellite. And with that, I guess I have time for a question or two?
I think we'll limit it to one, and then we'll take a break.
Okay, well, Martin, you had your hand up first.
If you envisage a mature SPS industry, what kind of fraction of the world's power needs would you imagine could be satisfied?
Well, I'm not sure if in principle you couldn't satisfy all of the world's power needs. You'd have to think about it and figure how you can satisfy all of the world's power needs with electricity, because not all of the world's power usage is electrical power. In fact, a lot of it is transportation and heating and various other things. But in principle, I don't see why the world couldn't be switched entirely over to electric power. If you were doing that, you would probably use a hydrogen economy, something that Peter Glaser alluded to a little bit in his talk, where the electricity is used to electrolyze water, and then the hydrogen can be stored and shipped and used for heating, can be used for transportation, can be used for the point source of electricity generation or just direct heat generation. At the moment, Earth usage is about 2 terawatts. The entire planet runs on about 2 terawatts. So at these gigawatt power stations, 2,000 of them would be required to produce today's power usage. But of course, out at 1.5 million kilometers away, that so small that you wouldn't really have to worry about filling up the skies with power satellites. Okay, Seth, I guess.
Well, I think we're going to take about a 2 or 3 minute break, and then we'll reconvene back in here for our next speaker, which is me. By way of introduction, I'm this guy, I work at this place, I do this stuff. The title, Bringing Space Power Down to Earth, should be taken in a variety of senses. Some of which are figurative, some of which are literal. Figuratively speaking, I'm going to try to do what my predecessor speakers and subsequent speakers are also going to try to do. Make it more a down-to-earth, immediately doable kind of project. In a slightly more literal sense, doing that may literally involve moving to a lower orbit, as Dr. Landis said. And in an even more, in a slightly less literal sense, bringing space power down to Earth means that one of the major design issues in an SPS is the need to bring the power itself down to Earth by beaming it. And as Jeff said, it's beam physics that is a major constraint. I think some of what I have to say is going to be review, and then some of it is going to be perhaps more detailed versions of what you heard before. This introduction, especially, I think at this point, is review. A, we need energy. B, we need lots of it, but the way we do it might have problems. I won't go into any controversies about exactly the nature of those problems. Solar energy on the ground is safe, but has certain limits with regard to intensity, intermittency, and so on. Therefore, we consider solar power satellites, and we will look at them from a point of view of power transmission. First of all, to put it into context, I will show for about the third time today the kind of SPS that we've spoken about for many years. This is a version of classic SPS, as Drs. Landis and Glaser showed you. It's a huge Manhattan-sized slab, and you see it. This is from The High Frontier by Jerry O'Neill. You see it in comparison to a Bernal Sphere Island 1 type space habitat. You see that it's huge. Again, for those of you who don't think metric and are into horse racing, this is about 25 by 50 furlongs. And as Jeff said, the transmitting antenna is probably a bit longer than the distance from here to the East River, namely about 1 kilometer. And the reason for this, again, has to do with the physics of power beaming. The reason that we talk about the spreading of the beam from an aperture being any kind of opening, such as a huge antenna array, is really the same phenomenon as diffraction. This shows what happens when yellow light passes through a 6 millimeter hole. I don't know how many furlongs yellow is, so you'll have to lift 6 millimeters. And a microwave passing through a transmitting antenna is basically the same as yellow light passing through a tiny hole, only on a much, much bigger scale. But the same thing happens to it, namely diffraction. Diffraction is the tendency of light to spread around obstacles, and due to the fact that the beam interferes with itself constructively and destructively, when you get away from the center of the beam, you see that you have these rings around it known as side lobes or secondary maxima. I've done a lot of calculations showing how you can minimize those, and they will have between about 16 and 1 in 16% of the total energy. This is an overexposed picture of a spot from yellow light. Most of the energy is in that central spot or main lobe. Here's my way cool Mathematica version of a microwave beam. Now, since this is a logarithmic scale, again, the side lobes are exposed, but it is the central lobe where at least 84% of the energy is located that is your design constraint. The bigger the aperture or antenna array compared to the wavelength, the less the spreading, and therefore that's why we have a huge 1 kilometer beam. And Jeff referred to the aperture law, and that is like this. And for those of you who read different languages, it looks like this. This law basically says the beam spot, which I'm saying is approximately how big you make your rectangle. We'd actually make your rectangle a little smaller. The beam spot can be made no smaller than the wavelength times the height of the orbit divided by the transmitter diameter. You can always make a rectangle bigger, but you can never make it smaller than this. This is a fundamental law of beam physics. The 2.44 is kind of a mathematical quantity that makes all the numbers come out nice. So I decided that based on the work of my predecessors, particularly Jeff Landis, I was going to set out to design the smallest possible solar power satellite. And in order to see how small you can get a solar power satellite, it really means how small can you make the rectangle beam spot. Because when the beam spreads, it's going to spread out to a certain size, regardless of whether or not there's 1 watt or billions of watts. And so you may as well put billions, and then classic SPS put 5 billion watts of that into the beam. Now the reason 5 billion watts was chosen is because when you work through this beam spot size and the shape of the beam, which Dr. Glaser showed has this kind of peak in the middle, you want the peak to be not too high so you don't heat the atmosphere, but you don't want the average intensity to be too low, because there's two problems if the beam is not intense enough. Namely, you're going to waste the land. As I said, you don't want to take up 10 kilometers worth of land and only put a couple of watts. You want to make good use of it and put billions of watts into it. The other thing is, if the beam is not a certain minimum intensity, which depends on frequency, but it's typically about 1, 2, or 3 milliwatts per square centimeter, you will not even be able to turn on the diodes in the rectenna, and you will not be able to convert that energy back into electricity. So I'm going to try to make the SPS smaller one step at a time by working with these quantities. And the first one I'm going to work with is wavelength. What can we do to make it? You can see if we make the wavelength smaller, we make the rectenna smaller. Well, what can we do about wavelength? Let's take a look and see what happens if we make wavelength smaller. And another way of phrasing that is we make frequency higher. Here's frequency from going up all the way to 100 gigahertz or 100,000 megahertz, going all the way down to this unmentionable number here. There's really no such thing as 0 hertz, but Cricket Graph didn't know that. Anyway, you see that what happens is when you send this beam through the air, once you get above about 10 gigahertz, the air starts to block the microwaves. But then things get better again around in the 30s, and that's why Jeff was talking about around 30 gigahertz, and some people have considered 35, which is where this window here peaks. But if you get much above that, things get really, really bad. Until at 60, you're really, really, really bad. But if you get above 60, up around 94, it kind of peaks again, although it's not all that wonderful peak. So you could perhaps choose anything. Classically, we consider 2.45 gigahertz, which is the same frequency used in microwave oven tubes. A lot of work has been done on that. We can up it to around 10, but if we want to go any higher than 10, we have to skip all the others and go directly to 30-something or 90-something, which sounds like a show about young professionals and their grandparents, but it really isn't. Now, I should warn you, there is a disadvantage to these higher frequencies, and that is when it rains, anything above about 5 or 10 is going to experience problems. Now, this 5 millimeter per hour is a typical temperate zone rainfall. That's probably the one you want to keep an eye on. Here you have thunderstorms, and those really can wreak havoc on a high-frequency microwave beam as the size of the wave gets smaller and smaller and closer to that of the raindrops themselves. They get more and more cut off. So that's one thing to do, and my recommendation in some of the studies I did was to consider frequencies up to around 10 gigahertz. Higher than that would be for more specialized uses in particular climates. Now, In order to justify calling this talk Bringing Space Power Down to Earth, I thought that the next thing we must consider is height. You see from this equation, or this inequality, that if we make the height of the orbit smaller, the rectangular diameter will get smaller, just as when you move a flashlight closer to the wall, the spot gets smaller. Now, imagine what happens. Reconsider that original classic SPS. You've got a 1 kilometer diameter antenna whose beam spreads to 10 kilometers, and I said you need to put billions of watts into that to make it economical and effective. Therefore, that's why you had a Manhattan-sized slab of solar cells. So obviously, if you're going to move that thing closer to the Earth, you can start chopping off solar cells and making it smaller. And in order to make this thing more bite-sized and at the same time make the calculation easier, let's pretend that instead of a rectangular slab, it's a circular slab. It really doesn't matter. It's area and mass we're concerned about. Now, notice that up here around 36,000 kilometers at geostationary orbit, you get an SPS diameter of about 8 kilometers, which is roughly equivalent to that 5 by 10 kilometer slab. And as you go down in altitude, you can see that the amount of solar cells, and what this is really is the size of the solar collector needed to get a sufficiently intense beam coming out of a 1 kilometer transmitting antenna array. Now notice what happens when you reach an altitude of about 4,000 kilometers. You now read across on the graph, and your solar array is now 1 kilometer diameter. Once you've reached that 1 kilometer solar array, you now say, aha, I'm going to go back and read Jeffery Landis' paper and say, now it is time to consider another way of making the SPS smaller and lighter. Not only smaller overall, but smaller in terms of mass per unit of power delivered. And two things come to mind. We use Jeff's suggestion and use that lightweight material, and I don't have a piece of it with me, so I'll wave the view graph, and it's almost the same stuff.
Right there.
Did it? Oh, okay. So you can almost put it on the overhead. Once you start using this stuff, the mass per unit power goes way down, and I'll show you just how far down in a few minutes. The other advantage is, now that I've shown you that the SPS solar array can be made as small as the antenna, what you can do is follow Jeff's suggestion and put the solar array on the antenna, or actually it's more the other way around, put the antenna on the solar array. So you can imagine something like this, dotted with little microwave circuits, and the microwave circuits and transmitters, which can just look like little metal strips, cover actually very little of this material. So 90 or 95% of this array is still collecting solar energy, and all of it is functioning as a microwave transmitter. So what that means is, getting back to Jeff's idea, is you have this hub and spoke arrangement. The entire array catches the sun, and the entire array funnels that energy to the Earth in the form of microwaves. Now, here's the good news, bad news about that. One idea to get most use out of this is it may be possible to cover both sides of this array with thin film of photovoltaic material. And I considered amorphous silicon, though as Jeff said, better materials may be available. The reason I considered amorphous silicon is the Space Studies Institute in Princeton, New Jersey asked me to come up with some sizes and masses, and they asked me how much would it weigh if you made it of lunar material as well as terrestrial material. But nevertheless, the basic system architecture stays the same no matter what you use. During the day, you can receive sunlight onto the solar cells on one side, transmit out the other side. At night, if both sides are covered with solar cells, then the same side is both catching the sun's rays and transmitting the microwaves, and the whole thing does kind of like that. Well, except the sun doesn't go like that. Anyway, you can see a couple of disadvantages. One is that you cannot simultaneously angle the SPS toward both the sun and the Earth at the same time, so you will have some loss in power. But I think a more serious problem is at dawn and dusk, which are times you might need power the most. You've got to flip this whole thing around, and for a few minutes you're going to be either edge on to the Earth or edge on to the sun. And if you edge on to anything, then you're not going to be able to receive power. So I'm not saying this is a showstopper. I'm just saying it's something that has to be dealt with. This is why the inflatable sphere concept has been proposed. And actually, I would suggest that if the entire sphere is made of both solar cells and microwave transmitters, then you always have a full cross-section of this hemisphere as receiver and as transmitter. Therefore, you never get that area loss as the thing goes edge on. Now, disadvantage is a sphere has 4 times as much surface area as cross-sectional area. So this thing has 4 times as much skin as a disc-shaped design. So it's going to weigh 4 times what it needs to. Now, it's not going to have that hub and spoke structure. The gas inside is going to weigh next to nothing. But even so, it's going to weigh per unit power delivered perhaps 3 times what the bicycle wheel design weighed. I sort of apologize for this rather cluttered next array. I looked at various frequencies and sizes and all this, and I realized if I show this, I'll be here until tomorrow. So I'm going to make that more concise and just show you a very brief summary of my study that I did for the Space Studies Institute. Everything on your left, looking at that line going up and down, is a thin film design. Everything on your right is a classic NASA DOE design from the 1970s. And you can see, it's hard to read these titles. This means bicycle wheel terrestrial, and next to each one is the lunar materials equivalent. Lunar materials, there's no polymers, there's no carbon to make the polymers for these substrates, so you have to use metal foils, so it gets a lot heavier. What this is specific power in kilowatts per kilogram, and you can call it calories per stone if you like those units, but the relationship between these bars remains the same. Namely, you see, this is bicycle wheel from terrestrial materials, bicycle wheel from lunar materials. Now here, I've eliminated, or at least reduced, that edge-on effect by adding a reflecting mirror. But a reflecting mirror could actually weigh more than the SPS if you want to angle it at 45 degrees and still see the sun. Therefore, when you add in the weight of the mirror, the unit power delivered per kilogram goes way down. Here you see with the inflatable sphere, you're also somewhat below the bicycle wheel design because, as I said, you've got 4 times as much surface as you do cross-section. But nevertheless, in any of these designs, you see you're much better off than you are with the old NASA DOE design. Now, given that, I want to go back to the old equation, which I've now buried under mounds and mounds of thin film view graphs. And if you'll bear with me for a second, I'm probably going to have to take up, I don't want to have to take up the next speaker's session rearranging my view graphs, so I'll just slap this on briefly. We've covered this, we've covered this. We can now go to this, but unfortunately 2.44 is equal exactly to 2.44 something, and you can't change a number. This is a fundamental constant. In fact, various schemes for trying to manipulate the beam can only make this number bigger. So now let's go to transmitter diameter. If you can make this bigger, you make this smaller. Now, what I did, in order to make the smallest possible SPS, is said, imagine you have a disk or a sphere that starts small and starts to grow. As it grows, it's catching more sunlight because you're increasing the solar array. But because you're also increasing the transmitter diameter, you're making this spot smaller and therefore more intense. So more and more power goes into a tighter and tighter beam. And if you set your ideal beam intensity equal to the NASA DOE intensity of between 20 and 30 milliwatts per square centimeter, then you get the size of the smallest possible SPS, which, when you combine that with the frequency increase to 10 gigawatts, turns out to be 2 kilometers and turns out to be a power level of about 100 megawatts, and it turns out to be a mass of about 60 tons. So you see, we've gone from the old DOE 5,000 megawatts and 50,000 tons to 100 megawatts and 60 tons. Ideally, it's about 15, 16-fold factor in power delivered per unit mass. And I think more importantly in the short run is it makes the initial investment a little more bite-sized, more down to earth, more of a small step in keeping with the theme of this conference. Now, as Jeff pointed out, you're going to need many of these things. What I just pointed out was for, in fact, geostationary orbit. If you want to go to low Earth orbit, and I chose 1,200 kilometers in the spirit of the Japanese SPS 2000 that Dr. Glaser showed, at that point, the size of the array goes down to 300 meters, the mass goes down to 2 tons, and the power delivered goes down to 3 megawatts. Now, as Jeff pointed out, you need lots and lots of rows of these. This is one version of an array of satellites known as a Walker constellation, and that's a classic way in which you deploy communication satellites. I decided maybe I don't like it that much, so I'll look at some other types of constellations, and these two struck me as particularly useful for the following reason. Notice that in B, on your upper right, you have 3 mutually perpendicular planes, each of which may have several satellites, but would even pay to have one at a time, because you see in the equatorial orbit, the satellite is very easy to track the satellite. It comes over your ground station once per orbit, and you can have lots of ground stations, spaced in such a way that as soon as one goes overhead, you lock onto the next one. Meanwhile, that one goes off and locks onto the next ground station. And ideally, if you have many of these, you can have continuous power. But, as Jeff said, you may need hundreds of them. So, have you really saved anything? Well, I'm suggesting that the advantage of this system is if you tap the right markets, even a partially deployed system can be economical, because you see that equatorial plane, that's where the developing countries are. Many of those people live in remote villages and they don't just use very little electricity, they use none. Some of those people, I think, may not even have seen an electrical device in their lives. The next speaker has been to such places, and he can vouch for this. So even a few minutes or a few hours of power a day might be useful. The other thing is, the reason I like those polar orbits is high latitudes are not easily accessible by geostationary satellites. So I see this as kind of a transitional phase between not having space solar power at all and having a fully deployed geostationary system or even lunar power system, as the other speakers will talk about. Now, one thing you need to do is, if you're going to use those high latitudes, space your ground stations in such a way that in one orbit, it'll go over this one. Then in the next orbit, the Earth will turn just enough to go over this one, and you can even have another row of ground stations below that, so spaced such that by the time it goes south, this is spaced just enough west so that when the Earth rotates beneath it, the minute the satellite loses sight of this one, it'll see this one. Then in the next orbit, it'll see these two, and you can have many of these. However, you don't have to in order to get use out of the satellite. I'll allude to something my predecessor said, a concept which John Mankins of NASA headquarters referred to as peak shaving. And this is much more primitive than Jeff's graph, but what you can do is deploy solar power satellites in sun-synchronous orbits, which are highly inclined orbits that come over at the same time every day, and therefore you can kind of fill in some of this demand that happens after the peak sunlight. And as Jeff said, you can even use the same piece of ground for both the satellite and the solar array. I mean the solar collector and the rectenna for the satellite. Now, in any of these systems, the way in which you deploy low Earth orbit satellites depends on the way, how many ground stations you want. This concept is known as quantized orbits. What you do is you pick the number of orbits you go around each day, and from that you can figure out how many degrees of longitude, the east-west spacing between each one. And once you know that, then the period of that orbit follows, and therefore the altitude that you need to put them follows. And you can see the limiting case being geostationary orbit at 36,000 kilometers. As Jeff said, that may not even be the limiting case. And in the spirit of talking about super geostationary orbits. I want to make the bridge between my predecessor's talk, where he talked about going beyond geostationary and going beyond the moon, and my successor's talk, who will talk about the idea of combining communications with low Earth orbit SPSs. And that's something that's more feasible with a low Earth orbit SPS. I want to show you an idea which I borrowed from Robert Forward, known as the statite. The advantage of a thin film material is if you put it far enough out, it can be held above the Earth by solar radiation pressure alone. You can see that based on Forward's idea, it's the statite is held aloft above the poles, which again is an area that geostationary satellites of either a communications or a power nature normally cannot reach. However, since Jeff showed you specific numbers, I must in all honesty say this is not to scale. I think you all know the satellite is not half the diameter of the Earth. That's not the thing that bothers me about this. What bothers me is indeed this thing is further away than the moon. Now, Forward realized this and pointed out that as a communications device, this is useful for data, but the problem with using it for real-time voice is that you don't want to wait several seconds for the person to hear you. There'll be a tremendous time delay because you could be about a light second from the Earth. However, the advantage of this is that for power, you don't care about the time delay. So I suggested to Dr. Forward that the solar power, the communications statite, be considered for use as a solar power statite. So I think I've kind of reiterated enough on the point that there are transitional phases between terrestrial solar power and a full-up geostationary power system. In a minute or so, I'll introduce my successor, who is really professionally my predecessor, who will go into that more. I think I'll take one question and then we'll have to move it along. Greg.
Yes, Seth. I actually have two questions. Can I combine them?
If you talk fast enough.
Very fast. First question. In the paper by Earth, Journal of Propulsion that you showed.
Oh, Brian Herb.
Yes.
Yeah.
It appeared that some of the rectennas were located in the ocean. Or is it perhaps that they are on islands?
I'm not familiar with Brian's paper, but Jeff had considered the idea in his talk in the last hour, and the Japanese have done some work on floating rectangles or rectangles anchored to the sea. So yeah, that could be done.
Now, the second one relates to this. The second question. Do you see any advantage, or maybe Jeff or Marty see an advantage, to putting a rectanna possibly on a balloon, a high-altitude balloon, and transmitting the cable down, the energy down through a cable?
I think what I'm going to do is, that may relate to what Marty's going to say, so I think what I'm going to do is clear my thin film devices here, introduce the next speaker, and I think after that, I guess what I will